This is the UE1, my 1-bit homebrew vacuum tube computer that I spent the last couple of years building entirely from scratch. Every PCB that you see on here was designed and machined right here in this shop. The paper tape reader here was built completely from the ground up. It is essentially me taking the concept of homebrew computing and running in arguably pretty dumb directions with it, but we did get to the point where this was actually executing code and running a program, qualifying it as a computer, which led a lot of people to ask a very pertinent question of, what can it do? Well, it can do more than nothing, but less than something. In order to understand where I'm coming from with this more than nothing but less than something statement, we kind of need to wrap our head around the architecture of the entire machine. And if we're going to talk about architecture, we need to talk about von Neumann architecture versus Harvard architecture. Now I'm going to boil this down dramatically here, but a von Neumann architecture uses a universal bus for both the data path and the instruction path. But in a Harvard architecture, the instruction path and the data path are separate. That means that an instruction can be a different size than the data that's being worked on. We have a 1-bit data path, so we're working on a single bit at a time. But we have a 4-bit instruction path, so we can have up to 16 different operations that we can perform. We also have an input enable register and an output enable register. This allows us to effectively mask input coming into the ALU and output going out to memory. And if we can mask those, we can effectively do conditional branching. Now it's important to note that every instruction is executed, but whether that instruction modifies memory or not can be controlled with this IEN and OEN register. Now, this is just the processor portion. This is just that left half of the board, and this by itself is pretty useless. So we need to put it in a part of a larger system. And you can see that we have a 4-bit instruction coming into the CPU and a 4-bit memory address. But we're actually combining this 4-bit memory address with the write signal coming out of the CPU. If the memory address is between 0000 and 0111, this is our random access memory. If the write signal is off, address 1000 is effectively reading the results register in loopback mode. If it is between 1001 and 1111 and the write signal is off, we're reading external input. I've got this set up as a bunch of toggle switches, but this could also be anything external to the system. However, if the write signal goes on, we are now writing to an external output register. For us, we've got this hooked up to a couple of VFDs, so that way we can see whenever we write a value to the output register. If we look at the instruction set here, we can see that we can load a value into the result register, we can do addition and subtraction, we can NAND or exclusive or, we can store and store complement, we can mask inputs and outputs, and we even have a couple of generic flags. This instruction set is very capable. You can run just about anything that you can think of with this instruction set. Heck, you could even run Doom with this instruction set if you had enough memory and enough speed. This is our bottleneck. We only have 8 bits of RAM, 1 byte of RAM. But that goes to show that the CPU itself is quite capable. The computer as a whole, though, is quite incapable because of our limited amount of random access memory. And when you're building a homebrew to be period correct to the 1950s, memory is the hardest thing to tackle. However, having 8 bytes of RAM is not nothing, which means that we can actually do some kind of calculations on this thing. So what's a good program that will actually stretch the legs of the machine? Well, an easy one to write up and test out is the Fibonacci sequence. The Fibonacci sequence is a sequence in which each element is the sum of the 2 elements that precede it. So if we have 1 and 1, we add those 2 together to get 2. Now we have 2 and 1, add them together to get 3. 3 and 2 equals 5. 5 and 3 equals 8. 8 and 5 equals 13. And this can continue on forever. Now, in order to write this, I'm going to split our 8 bits of random access memory in 2 to have effectively 2 different locations of 4 bits. That's the only way that we're going to be able to do this. And it also limits the highest number that we can count to. So to write the code for this, we're going to start off with just initializing the CPU. And to do this, we're going to do a 1, which forces a 1 into RR. Then we're going to load that into IEN and OEN, so our input and outputs are enabled. Then we'll do a NAND with RR to zero out the result register. Now we also want to zero out the scratch register and the output register. And we do that by just essentially storing the result register, which we know is 0, into all 8 bits of the scratch register and all 8 bits of the output register. Now we're going to cheat a little bit here, and we're going to do a store complement into the scratch register position 0 and the output register position 0. And this is because we know that the Fibonacci sequence has to have a 1 in it to get the ball rolling. If they're both 0, 0 plus 0 equals 0, 0 plus 0 equals 0 ad infinitum. Once we have that, we'll load operand A, which is bit 0 of the scratch register, into RR, and then we'll add that with operand B, which is bit 4 of the scratch register, and we'll store that result back into operand A. And then we'll go through and repeat this same process for all 8 bits of the scratch register. After that, we want to put the result into the output register, so we'll load up each of the 4 bits and store them one at a time. And this just continues over and over and over again. It's not a very graceful way to write code. I'm not a good programmer, but this is how we're going to do it all the way to the very end. Now, before we get too far ahead of ourselves, we should probably double check that the code that we wrote actually works. And the best way to do that is in an emulator. And I've actually written an emulator as well, but if you're sitting here looking at the screen in front of me going, what is going on? I like to program in Quick Basic. That's just where I feel comfortable. And a good friend of mine, Mr. Corey Smith, has helped set me up with an environment both on my laptop and on my desktop here. We're essentially running DOSBox with Quick Basic 4.5 here. So this is what I did all of the programming for both the emulator and the assembler end. So let's go ahead and open one of them up. We'll go to Open Program here, down here to Quick Basic Programs, and we'll open up UE1emu.bas. And this is my program. This is the emulator. It took me a little while to make sure that everything was working correctly, but I think I've got all of the bugs hammered out of my emulator program here. So we'll go ahead and hit F5. Comes up with a little prompt telling you how to run it. First of all, it asks where your assembly file is located. That's going to be in C:UE_ASM. Then it asks what the name of the assembly file is. It's UE1 Fibo. And now it's going to ask for a clock speed, and this is kind of not accurate. I didn't know a good way to do clock speed, and anything above about 50 hertz in here is pretty much roughly the same because we're hitting bottlenecks. But we're going to run it really slow because I kind of want to see what's going on. So we're going to run it at about 10 hertz here. And if we go, hey, there we go. We're actually currently running. So I'm going to press the H key so we can kind of get a lay of the land so we know what we're looking at here. We have a list of all of our registers: carry, results, input, output, enable, and then we have our scratch and our output register. And you can see both of those are storing a 1. So we're already pretty deep into the program. We have an input switch here, and you can actually control this using some buttons on the keyboard, but this program doesn't use that. And then below that, we have all of our generic flags. And it says processor halted, press any key to resume. So if I hit a key, it's just going to pick up right where it left off. And you can see our output is currently storing a 1. You can see our scratch register has now been split into the 2 operands. And now output has a 1, 0 in it. That's 2. Now it has 1, 1. That's 3. Now it has 1, 0, 1. That's 5. And then we go up to 1,000. That's 8. Then 1, 1, 0, 1. That's 13. Finally, 10101, it rang the bell, it halted the processor, and 10101 is 16 plus 4 is 20 plus 1 is 21. That is the correct answer. That tells me that the program is good, and actually it tells me that the emulator is working pretty well too. Okay, so we'll hit escape to get out of this. We'll go to File, Open Program, and we're going to go to UE1ASM.bas here. So we're just going to hit F5 on this one again. It's going to ask me for the location. It's going to be C:UEASM. The file is UE1Fibo. And then we just hit enter, creating binary file. Binary file creation finished. We now have a binary file that we can punch out. Let's see if we can get a look at it. I think I can go to exit here, and then we do a debug at c:/ueasm/ue1 fibo.bin. And if I hit a D here, yeah, I think that's correct. 40A8B858, and then we get to 80, 81, 82, 83, all the way up through 8BCDEF. This is going to be our store operations, because the store is 1000 in binary, and that's going to be the first nibble, which is going to be 8. And then the locations that we're storing, we start at 0000, and then we count all the way up to F. That's absolutely the correct binary. We created the correct binary. I just need to hook up my punch now and punch this out. All right, in order to send this binary file over to this Facet 4070 punch, we're gonna do it over serial. And because I haven't written a serial dumping program like that for Quick Basic or DOSBox, that's something my buddy Corey is helping me with, we're gonna do it over teraterm. So we have a little bit of header sticking out here. So we're just gonna navigate to File, Send File in teraterm here. I'm already in the right folder, and we're just gonna click on ue1 fibo.bin here, double check that it is a binary file. We'll click open, and it should start punching it out, which it is. That's awesome. Look at that. And it's not a very long binary file, so we'll give it a little bit of a trailer here. We'll cut it, and there we go. That's our whole program. It actually looks pretty short when I look at it like this. I was actually expecting that to be a bit of a longer program. Anyways, hopefully it all works fine. So next step is to power the machine up and give this a test. I've got the tape loaded up. We're pretty much ready to go. The only thing that's really changed since the last time you guys saw it was that I swapped out some resistors in the buffer up here that drives the bell driver circuit to ring the bell. But that didn't solve the problem. The bell still just kicks off and goes absolutely bonkers all on its own. I think the problem is going to be somewhere here in the decoder, not in the buffer, but I'm going to have to dig into that a little later. So for now, the bell is it's unplugged and unpowered, so it's not going to ring the bell. But what we're hoping to see is 10101, which should equal 21 on our little output down here. I've never actually tried running this program in here, so let's just go for it. Well, we got nothing in the output register. Dang it. Okay, let's see if we can figure out what went wrong. I am a bad programmer. I am very not good at it. I know just enough to get myself into heaps of trouble, but also sometimes get the job done. I sat down, I have this handy little cheat sheet here that shows me exactly what the binary code is for the instruction and for the memory address. So then I started looking at the binary to see if maybe there was a fault in the binary. And the binary was totally fine for the first like 20 or so bytes. And then all of a sudden it wasn't fine anymore. We can see that we do a load SR0, should be a hex symbol of 10. Instead, we're getting 24. Now, if we look at the very next instruction, and that should be a 24. So we somehow missed the load instruction. And that leads me back to my assembler. And here's where a lot of you, I think, are gonna cringe. We get down to our do loop and we do a line input on number 1, which I loaded earlier from the file, and we store that into NPC. And then we take the leftmost 4 characters and store that in opco for opcode. Now this is where the problem is. You can actually see it clear as day right here on this screen. Because I'm a terrible programmer, I'm also including the white spaces after the opcode because I'm reading up to 4 characters. But when we get to load, I only have 1 white space after. So I need to this is so stupid. I need to go up here, hit the space bar once, and that will now fix my code. And we can punch this out again, and all of my load operations should now be on the tape. And then we can run it again on the real machine, and hopefully it'll work this time. here we are again. Hopefully it works this time. At least we have our load instructions now. That's a good first step. So let's go ahead and just hit the go button and see what happens. Well, that's not right. Nothing on the output there seemed to change. Still got more troubleshooting to do. Boy, this thing has taken no prisoners today. Thankfully, I have the little single step panel that I can use for just this type of situation. And looking around, man, there's just garbage signals everywhere. 4.7 volts is all right for a logic low, but 10.5 volts is neither low nor high. That's not great. But we're still squarely in the information gathering stage here, which means a lot of toggling and looking at the voltmeter. Yeah, 4.1 volts again is fine, but 12.5 volts is very much so not fine. Initially, I was thinking this might be due to a double buffer problem. I meant to run 2 buffers in parallel for extra drive current to the memory select lines, but I accidentally wired them up in series, and since buffers aren't perfect, they'll be behaving funny in this situation. I don't think this is the problem, but it's a problem for sure, and it's a fairly easy one to fix. I just need to remove this little panel right here. Then I need to measure out where to drill the right hole for the new jumper. A quick run over to the drill press, and now we have the hole that should have been punched originally. And next I'll remove the original short jumper and drop in the new, much longer jumper. It was a simple fix, but like I feared, it was a problem, but not the problem. I pulled a ton of panels for testing on the bench, and this is one of those things where the whole is somehow worse than the sum of all its parts, because each one tests fine on the bench, except for this little guy here. It has a broken solder connection. I'm surprised this didn't crop up earlier, as it's residual damage from when the whole thing got knocked over in the wind several years ago. Again, that was a problem, but not the problem. Time to get the scope out. And yeah, that signal doesn't look good either. It shouldn't be defaulting to 10 volts in the middle, even though the logic low and logic high levels look fine. I think it's finally time to address another problem that's been bothering me though, and hopefully this will fix our signaling issue. Then that meant that it was time to fire up the mill and slice out these daughter boards. If a bodge is going to be obvious or on the front of the boards, this is my go-to solution usually. A daughter board totally looks the part and is often more reliable in the long term than stringing wires around. And speaking of those memory boards, let's go ahead and pull all of them out. And I'll need to do a bit of desoldering, which on a single-sided PCB with no solder mask is extremely easy to do. I need to remove this big power resistor, then this little 100k ohm anode resistor, and finally I need to pull out the little vacuum fluorescent display. And I need to do this for all 16 bits that I'm working on here. The 100k ohm resistor is going to get replaced with a 33k ohmer, and the power resistor gets replaced with a straight jumper. This is to move power down to the new daughter board. And I love machining stuff because things just line up perfect the first time. The daughter board slots right into place, and once everything has been soldered up and the tubes repopulated, you can see the new modification versus the old VFD solution in these shots. It almost looks like I originally designed it this way. It came out looking great. With all 4 boards soldered up fully, it's time to get all the tubes back in. I need to grab 16 new 6AU6s to fill the sockets on the daughter boards, which takes our total number of 6AU6s for the memory up to a whopping 80 tubes. And for those keeping score at home, the entire UE1 is now using a total of 324 6AU6s, 6 2D21s, and pulls around 675 watts of filament power. We're all back together now, and what has changed and why? Well, the only things that I've really messed with are the scratch register and the output register. This is our 8 bits of random access memory and our 8 bits for output. And initially, in order to save as much space as possible, I decided to build the flip-flop out of a 6AU6 and a VFD, or vacuum fluorescent display. This was a bad idea, although it did kind of work. But the reason it's a bad idea is because flip-flops like to be balanced. But I'm using both of those in ways that they're never intended to be used. The 6AU6 is a sharp cutoff pentode that is meant to have about 100 volts or more on the plate. And here I'm running it with just plus 24 volts. So already the 6AU6 is in a unhappy place. The VFD is actually a triode, but it's not meant to be doing any actual work. It's a vacuum fluorescent display. It's meant to only display stuff. So using it as half of a flip-flop means that if that balance between my unhappy 6AU6 and my misused VFD gets out of whack, the flop may not flip and the flip may not flop. It's just not great. However, these daughter boards here plug into the through holes for the VFDs, which have now been removed, and they actually make more effective use of the available space. I also had to remove and change quite a lot of resistors because I used some very weird resistor values to try to get that 6AU6 VFD combo to work, but I've gone back to just the exact same resistor values that I use for every flip-flop everywhere else on this board. So this should effectively work, I hope. I haven't actually put any power into it yet, so I have no idea if it's gonna go up in smoke or if it'll just start functioning. Well, it's powered up, nothing went up in smoke, so please work, baby. This is a big change. Hopefully we see something happen down here. Let's go. So close. None of that looked right, but we are pretty close to the correct answer down here. It should be 10101 and it's all ones. So we got something else going on here. Oh no. I put some extra pull downs on some signals over here that were not looking clean, and they are looking much better, but things on this end have now gotten exponentially worse. If I hit the button here, it runs through, we get a little blip on the output register, and then nothing else. I have no idea what's going on. The memory was actually working really well before, and it is still working really well. If I go through and I single step it with the toggle switches here, I can put a bit into each location of memory and I can read it back out from that. So maybe we're hitting a speed limit problem. I don't know. Every time I think I've got it cracked, like putting these daughter boards on, for example, I just seem to move the problem to a different location. Man, homebrew computing is just hard. That's all there is to it. Building a computer from scratch is one of the hardest things you can do. And if you're building a homebrew computer at home and somebody gives you guff like, oh, it would be so much easier to do X or so much easier to do Y, you can tell that person to go play in traffic because this is one of the hardest things anybody can do. And I'm now ranting. Mad respect to anybody out there that's building a homebrew computer because this is properly trying. I'm losing my sanity over here. So what we're gonna do is we're gonna set this thing aside for a little bit. I'm gonna take a break, take a deep breath, kind of reset my brain, and we're gonna revisit it at a future date. I really wanted this to be the final episode in the UE1 series, but looks like we got one more in the hopper. However, if you want to play with a UE1 that does actually work, I'll put the source code to the emulator in the description below. Massive shout out to Corey at gotbasic.com for helping me get through all of that. And well, right now that's the only fully functional UE1 because this guy's still fighting it. So I'm gonna keep slugging away at this thing over the course of the next couple of weeks. Hopefully we can find the smoking gun and get this thing fully running Fibonacci. So I want to thank you all so much for watching, and I hope to see you in the next one.